Hello Math 3311 students. Let's begin Lesson 11, Arithmetic Functions, Part 2. This is a continuation of Lesson 10, which covered up to Section 2. Lesson 11 begins from Section 3, Moebius Function. Here's a definition. Given positive integer n, let k be the number of distinct prime factors of n. Remember the fundamental theorem? Any positive integer can be uniquely decomposed as product of primes. If n is 1, then there's no prime, so k value will be 0. Otherwise, there will be some positive integer number of prime factors. That's going to be your k value. And then we defined the value of Moebius function mu like this. Mu of n is 0 if n is divisible by any square of prime, some square of prime, some p squared where p is prime. Otherwise, -1 to the k power. What is k, by the way? It's some number of distinct prime factors of n. Here's some examples. Mu of 1 is 1 because -1 to the 0 power. Remember, there's no prime factor. 1 has no prime factor, so 0 prime factor, k value is 0. How about this? Mu of 40 is 0 this time because 40 can be decomposed as 2 to the third power times 5 to the first power, 8 times 5, and consequently 40 is divisible by 2 squared. It falls into the first line. In fact, if you have a prime factorization, and if there's any prime factor with power greater than 1, that is power 2 or higher, then it'll fall into the first line, and mu value will be 0. It will be divisible by that particular p squared. Now, next two examples, we have 3 prime factors, but powers are all 1. So it falls into the second line, -1 to the k power, but k is 3, so -1 to the third power. In this case, again, 4 prime factors, and powers are all 1. So -1 to the fourth power because it falls into the second line. You can calculate like this. Whenever you have a prime factorization, you have a unique value of Moebius function. By the way, according to this definition, we get mu of 0 is 0 because 0 is divided by prime squared. Actually, 0 is divisible by anything. However, most mathematicians do not define mu for 0. They just define mu for z plus only. It's okay to define mu of 0 as 0, but I'll just follow the textbook here. I'm not going to consider it for z. I'll consider it from 1 or higher. Okay, so much for the definition and some examples. Let's consider some properties of Moebius function. The first property is a multiplicative property. It preserves the multiplication of any pair of positive integers that are relatively prime. And the proof, well, kind of brute force method, we just consider case 1, case 2, case 3. We have prime factorization where all the powers are 1. Oh, by the way, m and n are relatively prime, so prime factorization of m and prime factorization of n, they do not mix. They do not share any prime factors, so p part for m and q part for n are completely separate. And then if the powers are all 1, then you're going to get -1 to the r plus s power, which is equal to -1 to the r power times -1 to the s power by the exponent law. Consequently, we get mu of m times mu of n. Now, what if you have some power greater than 1? If any of this has a power greater than 1, then of course mu of this mn is 0, but it can be written as 0 times something where mu of m is 0. The same here. If one of the q's have a power higher than 1, then overall mu of mn is 0 because it says a prime factor with power greater than 1. And that can be written as something times 0, where mu of n is 0. So it works for all three cases. I should have said all four cases, as a matter of fact. In really trivial cases, when m is 1 or n is 1, then there's no prime factorization, just 1. But then again, in that case, we just have 1 times anything is just itself. So we get the result trivially. So in any case by case, it works out, and we have the proof. So the Moebius function is also multiplicative, and by the way, remember all these functions, sum and the number of divisors, sigma and tau, and mu here, and section 4, Euler's function phi, they're all multiplicative. Okay, we went through 3.2. Now the next property is 3.3, Euler's summation formula. Works like this. Sum of all mu of d, where d is a positive multiple of n, positive divisor of n, is either 1 or 0. Equal to 1 when n is 1, otherwise all 0. Some people write like this, which is perfectly legitimate, and I've seen some people writing like this. But I don't like it very much. This is a floor function expression, the greatest integer not exceeding whatever's inside, and inside is 1 over n. In a special case, n is 1, then 1 over 1 is 1, so we have 1. But otherwise, 1 over 2, 1 over 3, 1 over 4, 1 over whatever, they're all between 0 and 1, so we end up with a second line. I don't like this expression very much, so let's just move on. I'm not going to use this anymore. I just wanted to show you in case you encounter this. So we have to prove that sum of mu of d for all positive divisor of n is 1 for a special case n is 1, otherwise all 0. Now the special case when n is 1, there's nothing to prove basically. The only divisor of 1 is itself. And mu of 1 is 1. So 1 equals to 1, there's nothing to prove. We're going to assume n is greater than 1 so that we have prime factorization. And then we're going to prove that in the end you're going to get 0, no matter what. Now let's consider the divisibility condition to determine what are these. We have to have the same prime factors where the powers start running from either 0, 1, 2, 3 up to ni. Like this. If you have any other prime factor, then that's not going to be a divisor. And if you have a prime factor that exceeds di, then that's not going to be a divisor either. So the powers are running from 0, 1, 2, 3 up to ni. And consequently, putting this thing here, which I just highlighted in blue, right here in this form, we get the summation of this d is summation of this product. This is what we have so far. Now, let's work out one more. We don't have to consider all the di's from 0 to ni. You see, in order to get all the divisors, then this power can be anything from 0 to ni, 0, 1, 2, 3, 4 up to ni. But if it exceeds 1, then mu of that value is always 0. Remember that? If any square of prime divides this number, in this case d, then mu of that d is 0. So this doesn't go from 0 to ni, it goes from either 0 or 1. And this is a quantity we'll have to work out. Okay, we up to here. Okay, we up to here. So d re-expressed as this product through prime factorization, and then we don't have to consider all the powers, just 0 or 1, nothing else. At 2 or higher, you're going to get mu value 0. Okay, all right. How do you get all those different d values here for this quantity? Well, if the powers are all 0, then basically there's no prime factor. You're going to get just 1. And then what if there is one prime factor, which is power 1 and all 0? Well, in that case, -1 to the first power, and then basically one of those k prime is non-trivial and everything else all 0. What if we have, say, 5 prime factors? Out of k prime factors, there can be any 5 prime factors with power 1 and the others are all zeros. And then all the way up to all k of them, well, you can rewrite like this. For no prime with power 1 or 0, -1 to the 0 power, and then one prime factor out of those k, -1 to the first power, 2 prime factors, and then the others are all 0, -1 to the second power, you see? And this is number of distinct prime factors, and then 3 primes, -1 to the third power, 4 primes, -1 to the fourth power, and so on, up to, or k primes, -1 to the k power. You can rewrite the summation like this. So the quantity that I'm adding up, they're all the same. So the problem is, how many are there? How many different ways are there to have, say, 2 primes that have 1 and the others all 0 out of total k? Getting 5 primes with power 1 and the others are all 0 out of total k. If you use a combinatorial argument, you'll immediately see that those are k choose 0, k choose 1, k choose 2, and so on. Those are binomial coefficients. Say, for example, this one here, out of total k prime factors, choose 2 prime factors, say pi and pj, with powers 1, and the others have all powers 0, and then the quantity is -1 to the second power, so 1. And then the next will be k choose 3, -1 to the third power, so -1, kind of like that. So basically we have this. So if you use the binomial theorem, you can rewrite it as 1 times -1 to the k power. So 1 is hidden always, and then -1 to the 0 power. 1 is always hidden. Oh, no. Yeah, let's try it like this. Yeah, okay, it would have been better this way. Previous expression is not wrong, but it's a little bit easier this way. And here, 1 times 1 to the k power is hidden. Here, 1 to the k minus 1 power is hidden. They add up to k power. 1 to the k minus 2 power is hidden, kind of like that. And then here, 1 to the 0 power is hidden. But we don't need any of those because they're all 1s. That's how we get the previous expression. And if you use binomial theorem, you're going to get 1 minus 1 to the k power, and that's 0. So the conclusion, always we're going to get summation equal to 0 for all non-trivial case. The trivial case, n equals to 1, in which case we don't have any factorization at all. In that case, we have the first line. Otherwise, all 0. That completes the proof.